Hello dear students, welcome you all. In this lecture, I am going to start the next unit of this course, that is nuclear and particle physics, and the unit is nuclear models, right? So in this chapter, we are going to discuss different nuclear models, right? These different nuclear models were proposed in order to explain different features of atomic nucleus. We have gone through all these features in the first unit of this course. All the properties of atomic nucleus has been discussed, right? And we know very well that the atomic nucleus, right? This is the atomic nucleus. It consists of a positively charged core that is having the dimension of the order of 10 raised to power minus 15 meter, right? This core of the atom is called as a nucleus, and the electron are revolving around this nucleus. And this core, positively charged core nucleus, consists of protons and neutrons. You can see here, right? Protons as well as neutrons, right? Now, when we did different experiments, we study the different properties of different nuclei in the nature. Then there were different features of the different nuclei, like some nuclei were undergoing nuclear fission, some were undergoing nuclear fusion. The nuclei were showing radioactivity, emission of alpha, beta and gamma decay. So in order to explain all these features of the atomic nucleus, we need a model that is capable of explaining different features of the nucleus. So for that, different models were proposed, and the first one was the liquid drop model of atomic nucleus, right? And then after we have shell model, single particle cell model, collective model. All these models were there, right? So today we are going to start with the first model, that is liquid drop model of atomic nucleus. Although this model was very successful in explaining certain features, like it was mostly successful in explaining the nuclear fission, right? But it failed to explain other properties or other features of the atomic nucleus. So for that, then we developed another models, right? So now I'm coming exclusively to the liquid drop model. This model was, proposed in 1935 by a German physicist, C.F. von Weizsäcker. Carl Friedrich von Weizsäcker. He was a German physicist, and he was the first person who has proposed this model, liquid drop model. Now, the basis of this model is that this model compare the atomic nucleus with the liquid drop on the basis of certain property. I am going to discuss them later. And then after, the semi-empirical mass formula was also developed by von Weizsäcker. And then with the help of that formula, we were able to explain nuclear fission of different nuclei correctly, right? This model in fact was in later 1939, right? Modified by Bohr and Wheeler, and then we got a very good model. In fact, that was also liquid drop model, but that was very good model for explaining the nuclear fission, right? So here you can see the peak of an atom, and we have atomic nucleus here. Now you can see here, this is the atomic nucleus, right? And this is a liquid drop. Now, according to this model, these two things are analogous to each other, or we can say they are quite similar to each other in many properties, right? The first one is, we know in equilibrium state, the nucleus is nearly spherically symmetrical. Although we know it has quadrupole moment, we have gone through the quadrupole moment in first unit, but mostly we consider that the nucleus is spherically symmetric. Similarly, we know very well that the liquid drops of all the liquids, they are also spherically symmetric, right? Right. Now, we know very well that the nuclear forces that are responsible for holding these neutrons and these protons together inside the nucleus, they saturate, right? We have gone through the different properties of atomic nucleus, nuclear forces. So we know very well that nuclear forces saturate. They can act up to a certain distance. Similarly, we know very well that the forces which are responsible for holding the water molecule inside the liquid drop, they also saturate. And these forces are intermolecular forces, and they are also short range, right? Just like the forces of nucleus. But although nuclear forces having very short range, but in case of liquid drop, the range is higher as compared to this one, quite higher as compared to the nucleus, but we can say that these two are similar, right? Now density of the atomic nucleus is independent of its size. We know very well all the nuclei in the nature, whatever size or shape they have same density. In the same way, the liquid drop of a particular liquid, now I am saying particular liquid, right? If I am going to take different liquids, then the density will be different. So this is a distinction between these two also. But the similarity is, if I have a particular liquid, then the density of the liquid drop will be same irrespective of its size, right? Now we know very well that binding energy per nucleon, it is a constant for a given nucleus. It does not depend upon any factor. Similarly, the latent heat of the vaporization of the liquid. Latent heat of vaporization means the amount of heat energy required to separate water molecules from the liquid drop. It is also constant, right? So these two things are again similar to each other. Binding energy per nucleon and latent heat of vaporization, right? Now, if a liquid drop has attained some energy, it is a thermally excited drop, agitated drop, then it can release its energy by cooling, right, by radiating some of its energy. In the same way, if the nucleus is in the excited state, it can release its energy in the form of either alpha, beta or gamma rays, mostly in the form of gamma rays, and then it will come down to the ground state. So again, these two features are similar. Now, the forces that are holding these nucleons together inside the nucleus, they are short range nuclear forces, strong forces. But the forces that are holding together water molecule inside the liquid drop, that force is surface tension. So again, surface tension is analogous to the short range nuclear force. We know very well that nucleus can split into two lighter nuclei, right? In the same way, a liquid drop can split into two smaller liquid drops. So again, we have similarity. Two lighter nuclei can join together to form a heavy nuclei, nuclear fusion. The same way, two lighter liquid drops can join together to form a larger liquid drop, right? So these are some similarities, 6 to 7 similarities between atomic nucleus and liquid drop that are the foundation of this liquid drop model, right? Now I am coming to some differences between these two, right? Dissimilarities. As I told you here also, that the density of the atomic nucleus is constant irrespective of the nucleus. It doesn't matter whether it is carbon nucleus, it is uranium nucleus, it is nitrogen nucleus, it is gold nucleus. Density is constant and it is 10 raised to power 17 kilogram per meter cube. We have gone through it in the first unit. Now, this feature is different. If I am taking different liquids, then they will have a different density. It is not same for all the liquid drops. For example, water have different density, mercury have different density, right? Oil have different density. All the liquids that we see around us, they have different density. So it means this feature is different. The one more thing is a large fraction of the nucleons, I mean neutron and protons, they are present on the surface of the nucleus, right? Whereas only a few water molecules are present on the surface of a liquid drop. I mean, this feature is slightly different. There is a deviation. This deviation is due to the very size of a neutron and proton as compared to the size of water molecules, right? The one and important feature that is making the difference between two is the charge. We know very well that the nucleus is a positively charged body, but on the other hand it is a neutral. Water drop is a neutral body, right? It does not carry any charge. With the advancement, we have arrived at a conclusion that the nucleon inside the nucleus have a substructure. They are arranged in different energy levels, but there is nothing like that in case of a liquid drop, right? So these are some dissimilarities between a liquid drop and a atomic nucleus. So when you are asked about the liquid drop model of atomic nucleus, then you have to explain all these things. First of all, this liquid drop model was given by C.F. von Weizsäcker in 1935. Later on, this was modified by Bohr and Wheeler in 1939 with the help of semi-empirical mass formula, right? That I am going to develop in the next lecture. And then it was the most successful model in explaining the nuclear fission. Nuclear fission means when we have a large nucleus, let this is a large nucleus that is excited by some way. Now it's getting distorted, so it can split into two lighter nuclei with the release of some energy. So this process is known as fission, right? So this model, as I told you, it was most successful model in explaining the nuclear fission, right? So this was all about the liquid drop model of atomic nucleus, right? So in the coming lecture, I will go through the semi-empirical mass formula that has been derived after this model, right? So thank you very much.